Okay, hello everybody. Welcome to my talk. I hope you're all enjoying GopherCon Day 2 so far. I had a really interesting day yesterday. There were lots of really interesting talks. So who am I? My name is Stuart Murray. I'm a senior engineer at Form 3. I've been at Form 3 for just over 2 years, and I've been interested in Go for a very long time. I first really appreciated how Go does things with Rob Pike's talk about lexical scanning in Go, which he delivered in 2011 at GTUG Sydney, but I think I watched it about 2014. But I'm very interested in the way that Go does things for a long time now. So my talk today is about how we've implemented an optimization to our APIs. I work in the core payments team in Form 3, so a lot of things flow through the code that my team maintains, and this is an example of one of the ways that we approach solving these problems and how Go helped us on that journey. So, my colleague Adelina did a great talk yesterday where she gave a comprehensive summary of Form 3 and an introduction to who we are and our mission. So I'll give a brief summary today, which is that Form 3 is a platform powering the future of payments. So what that means for our customers, including some tier 1 banks, is that they can integrate against our API. They can then send and receive payments and do so in a standard way, which means if they want to use different schemes, they can do that in an easy way. And then they can focus on what's important to their business, and we can take care of the common headaches that allow them to focus on what's important to them. Within Form 3, we use a lot of Go. We have several hundred repositories, and many of them are written entirely in Go. And Go is a success story within Form 3. It allows people to join teams, move between teams easily. It enables us to work on microservices in a way that is quite standard, which means that people can get up to speed quickly, can move around as the company grows, and so on. So without further ado, the agenda for today's talk is the scaling problem itself, our approach to solving it, and our process for using Go. I'm also going to have a demo where I'm going to show what using Elasticsearch in Go looks and feels like, and our approach to overcome several of the problems as we took this into production. But generally speaking, we're going to start with the scaling problem itself. So this is a simplified overview of our infrastructure. We have a lot of other things going on, but for the purposes of this talk, we have our customers using our systems, making requests to our API. We then store the data within Postgres, and we have a queue which allows our microservices to read from Postgres units of work that need to be done, represented by messages in the queue. The services can then pick up the work, do the work, post new messages to the queue, change the database if they need to, and so on. So this works for us in terms of building a distributed system because it means we can have many microservices interacting together, and we can scale this quite easily. As we talked about yesterday, we can add new services and have fan out between services and so on. So it enables us to grow our stack as we do different things. So the key things here are that the queue is an SQS queue, and as I said previously, this is a very simplified diagram. Okay, so the problem itself was that we had customers who were making heavy read queries to Postgres. So they have an admin user interface that they can use. This allows them to track issues with payments and so on. So it's not direct customers, but it's customers of the banks and our support staff within Form 3 needing to do certain operations that require data to be retrieved from Postgres, joined, rendered, displayed, and so on. These queries were very heavy. And with the existing configuration, we were using a lot of the same tables, a lot of the same database infrastructure that we were using for the core payments flows. Now, payments within our systems need to be processed very quickly. So if we're having heavy reads on Postgres, this is going to slow down our ability to meet those required service level agreements, which is a problem. It also presented because customers themselves couldn't do certain of these queries because they were so heavy. So occasionally these queries would fail, they wouldn't get the information they needed on screen. So the objective, simply stated, was to take the load off Postgres. And how do we solve the problem? We had a number of different things that we'd considered when we were solving the problem. So first of all, we needed to know what the problem itself was. Now the main thing to say is that it wasn't that Postgres was bad or that there wasn't something that we could achieve using Postgres exclusively. But the core thing was that we had an architectural goal for our next step of our architecture, which we've talked about yesterday, but essentially we're wanting to be able to move between clouds and move away from Postgres to use things like Cockroach DB to enable us to do this. So, as I say, it's not a slight on Postgres, but it was part of our decision-making process. To start with on the left, we knew what our goals were in terms of throughput. We knew what the problems were, we could reproduce them, so that enabled us to frame our problem space. We could also build some tests that would allow us to know once we'd been successful. In terms of the solution domain, as I say, we'd looked at Postgres. We knew there were ways to solve this with Postgres, but we had Cockroach in mind. We had a new architectural evolution in mind. So it was an opportunity to move away from Postgres. We did consider a number of other products and technologies, and I'll explain how we settled on Elasticsearch. But essentially, we did consider a wide range of different technologies. Within the organization, as I say, we had the architectural roadmap of where we were going to be more cloud agnostic, move away from hosted Postgres on AWS and move towards a Cockroach cloud native multi-platform architecture. And we also had expertise within the organization. We'd used Elasticsearch previously. We knew what we were going to get out of it, and so it was a good fit. Finally, we made some final design approaches and some proof of concepts, so we knew that the performance was going to hold up. And again, we backed that up with rigorous benchmarking to ensure we had a good architecture. So the result of all of that process was that we came up with a selection of Elasticsearch. We've got a nice shout out here to the Form 3 Tech podcast that I added. I found this episode particularly interesting. But essentially, Elasticsearch can be configured to work across multiple clouds. It's very, very amenable with our architectural approach. In terms of Elasticsearch itself, why it fits our needs, it works as a document store, and I'll explain how that works in a couple of slides. But it's an analytics data engine, so we can put information in there and we can retrieve it in a number of ways. Elasticsearch understands the payments we're giving it to store. It can project and display them to help us with our UI, but it's also got very powerful query enhancements. There's a lot of different things you can do with predicates. I'm going to show very basic queries today, but there's a lot of very sophisticated querying you can do. Ultimately, the lineage of Elasticsearch is that it is a search engine powering database. Okay, so starting from the data level, on the left here, we've got a record that we would store within our database. So a payment has an ID, would just typically be a standard GUID. The user would post that to that URL, and then we would be able to model that in Elasticsearch using a payment. So again, we'd store it against the same ID. Typically, we'd then store key information about the payment. So within Postgres, quite a lot of our information is already modeled as JSON-B, so it's quite a simple transformation just to map similar JSON stuff into Elasticsearch, but we also have some fields in the record that we might project as well. But the ultimate output is a document that we can store within Elasticsearch. So that would enable us to solve the insert case. In terms of updates, customers are going to be putting to the URL the changes they want to make, and we can enable that by putting the entire new document in Elasticsearch. We can do small changes as well, but we typically replace the whole thing because that makes it easier for us to reason about this whole document is version 1, this whole document is version 2, and so on. In terms of related information, payments in our system would typically have accompanying related documents. So in this case, this is a payment that's come to a customer of Form 3, going to one of their customers. So it's admitted from the payment scheme to Form 3. So this is where the power of the Elasticsearch approach comes in, because we can embed that admission within the parent document. So we know if we retrieve this payment, we can retrieve the related information really easily. There's no joins, no extra performance overhead, and we can just render that straight to our UI. So that was really helpful for our use case. So this gave us the broad strokes of our architecture. We were going to have a Go microservice that was going to be able to consume messages from the message queue. It's going to be able to project them to produce documents, which represented the payments, which would then be able to store inside Elasticsearch. We'd then move the reads to Elasticsearch, and that meant that the performance impact on Postgres was minimized, and that all of the heavy read load would go to Elasticsearch. So this diagram is a really good demonstration of how the Go microservice that we were going to implement is working at a systems level. It's right in the wheelhouse of what we want Go to do. It's reading directly from a message queue, working natively with cloud-native primitives. So we're reading from a queue, writing to a data store. Everything is free of a UI, running in a really robust, resilient way. And we just thought it was a really, really strong fit for Go within our platform. Okay, so there's a few useful things that this architectural approach gives us. So the first one is that it's unidirectional. So what that means is that the payment API and the Postgres database are the source of truth, and the changes come from there to the queue, go through our microservice, and then get affected by the puts that we do to store the new data in Elasticsearch. So this unidirectional approach gives us a guarantee that if we have information that changes in Postgres, if we change the Go code and we need to represent the data in Elasticsearch in a different way, and basically as we evolve the design, we can just replay the data from Postgres through our queue again and into Elasticsearch. And that gives us the ability to evolve the schema as we need to, as our needs change. It also gives us the ability to verify what's happened. So we know how our first Go microservice works, and we can build a second Go microservice reusing a lot of the code. And again, this is why Go really helped us. And that service can understand what's in Elasticsearch. It can understand what would have happened in Postgres. It can compare the two, and it can give us alerting and monitoring if our microservice isn't working properly, and we can take action to fix things. It can also help us with the initial sync. So we can have a third microservice, again sharing a lot of the Go code, which can read from Postgres, know what the events should be, emit those to the queue, and then we can populate them to Elasticsearch using the first microservice. So not only do we have the ability to detect problems and to change our schema to solve them, but we can use this service to move data into the new approach, and also as we need to redo projections of data, we can also run this microservice. So we're using a lot of Go here already. I'll keep it really simple in terms of how the client works, but I just wanted to give people an overview. Finally, we've got other architectural options then. So we've not necessarily taken this approach for this microservice, but we have the ability to use NATs and to work in a multi-cloud way, and we can also look to potentially replace Postgres with Cockroach. And this approach is an architecture that we can compose, and we can work across different clouds and different approaches. So yeah, I just wanted to give those 4 key benefits of the approach. One key thing here is that NATs is clustered so it can heal. With our microservice as well, we run multiple instances of it. And again, the unidirectional approach, the fact that we've got good observability and so on, all these things mean a lot of this architecture can heal itself. Okay, so now we've given the brief overview of the architecture. Why did we use Go in particular? So you may have seen the talk that Uber did at GopherCon 2019, where they talked about how Uber does Go. And there have been other talks at this GopherCon where we've got other approaches to taking problems, building microservices from them. We've got our own approach within Form 3 as well. So similar in some ways to Uber, although Uber use a lot of dependency injection in their approach, we have tools that can build Go microservices for us and bootstrap them so that we can focus on what's specific to our problem. So we do put these on form3tech-OSS on GitHub from time to time. So keep an eye out there for tools that you might want to use. But generally speaking, for this service and similar ones like it, we use our in-house templates and our in-house libraries to give us a number of benefits. So that can mean, and this is a point which will be interesting to explore, it can mean that some of the microservices that we create might be slightly more complex than they need to be, but that an engineer within Form 3 who understands our approach can move between different microservices really easily. We have a logical place for code and so on. I'll get to the directory structures in a moment. Okay, so this slide with the Go emoji, it wouldn't be a Go talk without a nice one. Go helps us in a number of ways. I've called out a couple of really nice Elasticsearch clients at the bottom here. But essentially, within the problem space itself, as I've said, we're reading from a message queue, writing a small microservice to consume the messages, and then we're emitting those to Elasticsearch. So it's right in the problem space that Go is trying to solve. For our teams generally, Go gives us a great developer experience because it avoids the accidental complexity that you might experience in other languages. We find it's really easy to scale. Again, we've talked about things like the JVM previously in other talks, but essentially we can put more stuff on less architecture, which is always handy, especially when you're doing the initial migration work. And, of course, there's a great community. So this is mirrored in things like the tools, but it's also the culture that we have within the company and the engineers generally that I've met who work in Go. It's really, really good. Everyone's quite egoless and quite willing to admit when they don't know things. It's the same in other languages too, but in Go in particular, everyone is very, very friendly. In terms of the testing approach, we found that Go allows us to work in a really lightweight way. Because the services are quite small, easy to reason about, and so on, we can adopt different testing approaches. So generally within Form 3, we would have tests which would be testing the overall integration, the interfaces between microservices, and we can definitely work in that way really easily using Go. It's also very easy to set up new microservices, new testing, and so on. And for Go itself, excellent standard library. As I said, the multiple Elasticsearch clients. So I'm going to talk about the Elastic one today, but there's also another really good one, this Oliveri Elastic client, depending on your needs. People have talked about Cobra previously as well, but this allows us to make microservices that are really easy to control, understand. And then we've got other tools that we use when we're building code. Things like GoPhumped and other tools allow us to have very strict linting. Everybody hates the linter, but everybody loves lintered code. So we can work in a way that is, again, really easy to collaborate, really frictionless, but also when we produce the code, we have confidence it's going to work and be maintainable. So folding that into our design process. As I've said, Go is about composition. And essentially what we're looking to do is have a number of elements which should be common in a lot of Form 3 microservices. So in this case, command handlers and commands allow us to implement the CQRS pattern. Sometimes we don't need that in a given microservice, but if we implement things as a central bootstrapping main.go, bringing things up, firing commands off to the command handlers, and wiring things up in that way, even though it is potentially a little bit heavier than you might do if you were implementing a one-off microservice, it means that people can understand where the code lives, how things are joined together, and so on. And critically for our implementation here, we have the strategy folder, which enables us to evolve the various strategies as we're storing different information in Elasticsearch. So we know how to map from given documents to given projections. We have one place we need to go if we need to make the critical changes to the code most of the time. We've also talked previously about pprof. There was an excellent talk yesterday about the deadlocks in Go. We can deploy pprof, we can deploy gin routing and so on when we're building our microservices as well. So this makes them very easy to command, control, and debug. As I said previously, if you were doing domain-driven design, you might organize by role. If you were writing a one-off Go microservice, you might not have all of this architecture as well. But we find that building our services in this way keeps them standard and keeps them maintainable. Okay, so I'm going to move on to a demo now. What I'm going to do to start is take you through the code that we've written. So I've got a number of Git tags, and I'm going to walk through those. But here we have a simple Docker file, which is going to build an Elasticsearch container. So very, very simple. We can typically run this in a clustered mode. So we'd have a master node and multiple worker nodes, and we'd link those together. For the purpose of this demo, I'm going to keep it really simple. Very simple single node network, data volume, and so on. So I'll get that running. I've also built a make file, which is going to help me with some of the tasks here, just to minimize typing. But whilst that's starting up, you'll see some output from Elasticsearch. So we capture most of this in our observability things in Prometheus, and we also have an elk stack that we use. So we typically be looking at the health of Elasticsearch, and I'll explain some of the output that we can get as well. But this is the general bootstrapping process. So we've now started Elasticsearch, and then within the make file, I have a number of commands that are going to help me to demonstrate how we might interact with Elasticsearch. So for now, just taking the Go code out of it, just to give people a flavor of how things work. So the first thing to do is I'm going to get the indexes. And this information here is what we typically would output when we are doing our monitoring. So what we can see is we can see the health of the nodes in the cluster, and we've got a yellow one here for our payments index. That's okay, because for the purposes of this demo, I'm only running one primary node and one replica, which is on the same node. Typically, we would run multiple nodes, and this is where we get into topics like sharding, which I'll talk about in a moment. Generally speaking, you want to keep your nodes green. If they're going yellow, and particularly red, then Elasticsearch will do things in order to preserve certain other guarantees. So generally speaking, Elasticsearch will sacrifice read performance to preserve write performance. So if your node is going red, you'll see problems like being unable to write to Elasticsearch. We've got lots of monitoring around this, but I just wanted to make it clear that you can get this output from the API, and we'll be doing that in Go in a moment. So next thing to do is to post a payment. So I'm just going to truncate it, just to drop the index there. Elasticsearch is telling me with the REST API that there's nothing there. Now I've got a simple document which is going to represent a payment. So we've talked about this previously, but what we've got is we've got the ID of the document, the payment amount and currency. Typically we would express that in the pence or cents here. Then we've got beneficiary and debtor information. They've got bank details there as well. So in the make file, we can then post the payment. I'll put the payment, sorry. Elasticsearch has told us that that's been stored, and then if I were to get the indexes again, you'd see it's stored, and then if I get the payments, this will pretty print the output that's in Elasticsearch. So we have a single document stored, it took 3 milliseconds to retrieve it, tells us information about the shards it queried, and so on. So again, this information would be stuff that we would review when we're tuning Elasticsearch and making sure that the performance of our system is good. But I just wanted to give the overall approach to how we're going to use Elasticsearch. Okay. The other things that we've got in here just to start with would be things like our Readmes and so on. Typically within Form 3, when we've got our code, we would have architectural decision records in here as well. So as a new engineer, if you were coming to a piece of tech, you could look in here and you could figure out some of the design decisions that had been made, as well as checking the commit history and so on. So let's evolve that a bit and add in some Go code. And we'll add in some models. So this will allow us to understand what's in Elasticsearch. So the first thing here is an external models struct. This represents what would come from the SQS queue. It's very close to what I've shown you in terms of what we've been storing inside Elasticsearch. It's just using simple JSON primitives. This would be fine for representing the data in Elasticsearch as well, but what we would typically want to do is to use models that are slightly richer. So I've used a money type here just to illustrate that, but there are other approaches as well. Typically here, we've got things that make sense to us when we're applying business logic. So we'd be looking to say, transform the money in such and such a way, basically applying the updates from the SQS queue. And by enriching the model from the JSON into this approach, then we can reason about that more easily. So between the two, we have a mapper. In this case, it's extremely simple. We're just saying that we're going to retrieve the payment. In this case, it could be from Elasticsearch or from SQS. And we're going to be able to convert it to a type that we can use within our domain. So far, so good. What we'll do then is we'll actually use the models. Okay, so in this case, we're building a simple Elasticsearch client. So we'll revisit this a couple of times through the talk, but essentially we would be able to encapsulate the standard client within our own struct, and this would give us additional control that we could add. I've not added this to keep the code really simple, but we could add extra state logic to say, is Elasticsearch currently unhealthy? What do we know? And we could potentially implement things in this code here that would allow us to back off when we're calling Elasticsearch, make intelligent decisions about how we would gracefully degrade our connections and so on. I thought it's worth adding that just to explain why I'm not using the client natively. We would then embed that client within the struct, as you might expect. And then here we're going to do a simple command to read the info from the cluster, which I've already shown from a curl interface. And then we're going to be able to display that on screen. So we'll just print that out here. So in the main.go, in this approach, we're going to have a simple main method, and I'll keep evolving this. But in this case, we're going to go ahead and we're going to get the cluster info. So build and run. And we've headed off to the server. We know our client version is version 8 from the go get repo, and we also have heard back from the server running in the Docker file. So the container is telling us that that is 7:15. So that's a successful round trip. So we understand the basics of how we might talk to Elasticsearch using the client. One other thing to talk about is the interface here. We can use a more advanced interface with the mappers, but for things like rendering the cluster info and the errors, to keep the example simple, I'll just use this map of string to interface. Generally speaking, though, we would always be rendering this to structured types. So that's the basics of how we'd use Elasticsearch. So moving on, we've now got the basic server info, which I've shown, and then we're going to do some of the core operations that I've been talking about today. So again, I'll just check out the next version. And we're going to create a payment document in Go code, and we're going to index that. So we've added a new external model that allows us to understand what Elasticsearch is telling us when we want to save a document. And we've modified the client in more detail to enable us to take in a payment, convert it to JSON, send an index request to Elasticsearch. So we're telling Elasticsearch, please store this in the payments index. Please use this body JSON document, which then we can use when we're querying it. We give it an ID that Elasticsearch can refer to the document natively. And then in this case, we're telling Elasticsearch, please ensure that before you tell me that the request is done, the document is going to appear in all indexes. I'd recommend using that for demo purposes to keep things simple, but in production we would not set this because we want Elasticsearch to be able to tell us that it's accepted the query, but we don't want to affect read performance by making the system wait. So I just thought I'd add that for the demo. Okay, so we're going to send that to Elasticsearch. We're going to get the response back. We're going to understand that using the external model that we've defined, and then we're going to emit that on screen. So we'll go ahead and do that. Oh, before we go, we've also got in the main file now a simple helper function that will drive all of that code, and then another method that will build a new payment for us. So again, we've got nothing useful in here. We've got the payments which I created previously with blue and green, and then if I'm running the new implementation we've built, we'll see that we've got the 201 response, and then we can see the new payment document created as well. So it's that easy to use Elasticsearch to write documents. So how about reading documents? That's also pretty simple. So we have a new external model again. This is going to enable us to tell Elasticsearch we'd like to retrieve some data. We can evolve this in a number of different ways, and there are a number of different client libraries that have taken this further. But for our case, we're going to tell Elasticsearch to give us the documents with a simple equality query. We've also got a find response that enables our code to understand what Elasticsearch is saying in terms of how the process of finding the document worked. I'll take you through this, but essentially it's telling us some metadata about how Elasticsearch was able to service the query, so whether it was successful at all or if it timed out, how many milliseconds it took, how many shards it needed to use, and so on. All this information is really important to us when we're tuning things, but it's not critical for the purpose of this demo. I just wanted to explain why it's there. The big piece of information that is useful to us is the hits. We get a list here of the different payments that match. We can then expand the client to have additional code to find the payments. So we can express the query in a number of different ways. The key thing to note here is that Elasticsearch is allowing us to specify a key path. So we can not only say we need documents with a beneficiary, we can also specify the name, we can work in terms of our domain and specify payment amounts and so on. This is really important to us. We can expand this in a number of different ways, and that allows us to do a number of very interesting things with our domain logic. Essentially, we can find documents in any of the ways that we might want to, but which we couldn't do quickly using the old approach. Once we've got the response, once we know what we want to request, we can build the request in a nice, easy way. We found the Go client to be really well written. So you've got option builder patterns, all of the nice stuff that you would expect to see from a modern Go framework. And it enables us to build requests easily and work the way we want to work. Once we've got the response, if there's an error, we can understand that. Again, just keeping it really simple for the demo. And then in terms of the happy path, we can decode that into a payment, and we can render some information about the query itself and about the payments that we've received. All this code is going to be available on GitHub as well, so don't worry too much about the fine details, but hopefully you've got a good impression there of how that's bolting together. And then just to go back to the main.go, we've got find payments here. Real easy to use. We're just going to call that find payments method with that hard-coded query in this case, and we're going to print a separator. So let's go ahead and do that. Okay, so we've got the output here. We've been able to understand the payments. Obviously, we don't render these to the terminal all the time. We'd be using these for other things. But just to prove here that we've mapped these across to Go real easily, rendered them to screen, and so on. So we can do everything we need to from here. And it was that easy to get started with Elasticsearch. We really found it straightforward to use. It worked really well with the way we do things. Just wanted to give people an impression of how easy that was. So we've also got some more stuff in the demo. So we've got some basic concurrency. I think I've just about got time for this. Yeah. So if we have a look, we can do a number of other things as well. So Go allows us really easily to do things like modifying the client further to take in a list of payments. So this allows us to index an array of payments that we can pass in a nice variadic way, and we can use Go routines to really easily say, do this work in multiple coroutines, send the information, use wait groups to keep it all synchronized, and so on. Now, the deadlocks talk yesterday has made me think that there may be possibility of things that we want to check in here. This is a basic, simple demo, but for production code, we would definitely check race conditions, all of the usual tooling that we would expect. But I just wanted to show again just how easily Go with the channels and the Go routines and the wait groups can allow us to do multiple payments being indexed. And then one final thing that I wanted to show was if we add the versioning to the payments that I've talked about previously, and then we implement a strategy. This is a very simple strategy. But what we could do is we could read from SQS or another data store. We could take a payment and we can transform it. And then critically, we can version it so that we know if the payment has already got a different version to the one we might expect from SQS. We can reject it. We can retry in intelligent ways and so on. If the payment is not contested, we can update it and work in that way. So these strategies allow us to evolve as we are representing different bits of data in Elasticsearch. And I just wanted to give a basic overview of how that fits together. Okay, so that's the end of the main demos. In terms of talking about wrapping the client, we've got the ES transport, which is available to us within that framework. And that enables us to query Elasticsearch generally. So what will happen is if Elasticsearch is having problems servicing our queries because of load, we'll be getting 4 to 9 responses from Elasticsearch generally. It will be telling us, stop querying so rapidly. The server needs a bit of time to heal the cluster, that kind of thing. So ES transport allows us to programmatically do more low-level queries of the framework that I've just shown. It's part of that framework. And we can say, what's Elasticsearch currently doing? What do we know? And make intelligent decisions to make our service more robust. So I'm not going to go into too much detail there, but essentially we've had a number of issues with the cluster. When we started this project, we knew about Elasticsearch and clusters generally, but we didn't know about our specific problems, our specific load profiles, and so on. So we've had interesting discussions with AWS in particular. They're running our hosted Elasticsearch at the moment. And some of the discussions have entailed things like, how many shards do we really need for our loads? What exact ratio of reads to writes do we have? And so on. So we've been able to use information like this, as well as the monitoring we've had, in order to very carefully customize exactly how we're using Elasticsearch. Yeah. So then this is an overview of the shard sizing that we might have in a typical environment. So what we do, you can see here we have payments indexes named by date, and we would be able to age out data as it is no longer relevant. All of this data is derived data, so if we need it again, we can get it. And certain payment workflows would need information that was quite old, for instance, chargebacks or recalls of payments. So we'd need to potentially get this information again for a small amount of our working set, but generally speaking, we can age things out. And by implementing code to manage these indexes, we've been able to keep the overall size of our live working set, that payments v1 Elasticsearch cluster, down to a manageable level. We were also able to control the number of documents per index in the working set, and again, over time, the number of documents would fall away as things become less relevant. So there's a trade-off between having more shards and having more resiliency, and more shards is more throughput, and more nodes is more resiliency. And if you have too many shards per node, that can cause performance problems. If you have too few, then you can be excessively burning money. So there's definitely a number of corner cases and edge cases as we've gone through the shard sizing process. Go hasn't helped us with that directly, but by keeping the client as simple as possible and by keeping the way we're working with it as simple as possible, we can focus on these system-level problems and not worry about our application code. Okay, one other thing to talk about is the feature toggles that we've built into our system. So, in other environments, this can be implemented in a number of different ways, but the key thing to note from this diagram is that there's a critical path here. So we need customers to be able to post payments, and for our purposes, the service level agreement might be a matter of hundreds of milliseconds. So if we put things on our critical path to help us with feature toggles, if they're open services, your launch Darkleys of the world or what have you, they're excellent services for certain use cases, but within Form 3's use case, if we put that on our critical path and they have an outage, that can affect our payment flows. So within Form 3 itself, we've built things within our infrastructure for this service where we can deterministically check environment variables and we can map requests dynamically between Postgres and the new service. So we've been monitoring this during the deployment of our service, and this has enabled us to do things like saying, how many times when we did a read did we not see the correct data in Elasticsearch? If the answer is not favorable, we can look to turn the feature toggle the other way. But we didn't use automatic canarying or anything else. We were just extremely carefully monitoring this service during deployment. But the key thing is, by building this stuff in-house out of simple Unix primitives, simple ingredients, we're not putting anything else on our critical path other than code that we understand, we know the performance metrics, and so on. So this approach broadly fits in with the way we do things within Form 3, which is that we've got a really intelligent platform, and we put a lot of our effort into making the logic live in the platform, which keeps our services quite simple to reason about at least. Okay, so turning to the implementation experience itself, I've already kind of set the stage in terms of how Go helped us, but what it actually meant on the ground were that we could build the project with a compact structure. As I say, everything had a logical place. It meant that we could use a minimal amount of code. Things were quick to produce. We were able to turn the project around to hit a deadline. And we found the code to be easy to optimize and to maintain once we'd created it. So it was a major win for Go. I'm going to show some performance graphs now, but I know these things can be quite muddy depending on how you interpret them. So to give you an extremely big picture, before we deployed the service, during quiet periods of time, the system was happy, it was running. During periods of load, system performance was reduced, and potentially we could fail to hit service level agreements if that load drops too low. And critically, reads weren't happening in a way that was helping our customers. Once we made this performance improvement, and this will be clear from the graphs, but basically, it didn't matter if the system was under load or quiet and we were doing these queries. We could also do the customer queries, and we weren't seeing throughput being affected. So zooming in from that big picture, this is an example of what this would look like in one of our environments. So this is one page of several for the metrics that we'd be collecting and monitoring when we're using our system. And the key things to draw you to here are the fact that we have regular jobs using our HTTP stack to query the Elasticsearch. You can see that cadence there. You can see that sometimes we have large loads and the search rate, Elasticsearch is able to keep up. The request times are really nice and low, which indicates that we've got the cluster size right. Again, the search latency, some spikes, but again, it's extremely low. And the overall response times to render results to the UI are also well within acceptable levels. So this is what healthy looks like. And we've had a number of times when it hasn't looked this way, and we've had to figure it out. And by working in Go, we've been able to do that because we can focus on the Elasticsearch problems and not the programming problems as much. Another slide to show is, again, another overview. And this gives us details of how the mapping is going. So requests are coming off of our queue. We have them batching 50 or so requests a second. We can see that Elasticsearch is able to keep up. Again, this indicates that our cluster is right-sized. We have occasional spikes. This is OK. And we have occasional spikes in Go routines again. So we have a number of things that we might look for and patterns that we've spotted over time. Typically, they can be to do with things like the Go clients don't release properly if Elasticsearch is giving 429s. They do have back-off code within those clients. But again, this is where we put investment time in and make decisions around how we can make our system more resilient day to day. OK, so that's the main meat of what I wanted to talk about today. Got a couple of final slides. I guess the first one is, feel free to have a talk to us. You can talk to me, or we're at the stand outside. But these are the sorts of things that we deal with at Form 3. So hopefully I've given you an idea of how we go on that journey with each of the problems that we solve and how Go has helped us with that. Hopefully you've taken something from the process that you can use in your teams or generally. And then before I wrap up, I just wanted to say thanks to everyone for attending. It's great to see people. This is my first GopherCon talk. I've done a few other talks, but I've felt really welcomed by the community, and there have been a lot of really inspiring talks. It's really a great community to be part of. Okay, so we've got a bit of time now for some Q&A, if there's any particular questions you have.
Hi, thanks for the talk. I was wondering, for financial transactions, how did you secure Elasticsearch for privacy and also prevent data leaks?
Sure, that's an excellent question, thank you. We've got a number of solutions in place in our stack to make sure that our customers only can see the data that's within Elasticsearch. We've got a dedicated platform that's making sure that requests that come to us have the appropriate signatures. So requests can only be made by people who've already gone through an exchange process with us. They make those requests. We can then use a number of systems that we've got to make sure that they have the ability to make those requests, that they're properly authenticated, we know who they are, and all the permissions are good. And then we go from there to Elasticsearch. So a lot of this stuff is done at our infrastructure level. And we've got a number of different systems within our stack that help us to make these decisions. So we have authentication providers that can store who can do what, and we can query those as we're making these routing decisions. Yeah.
Hi, thanks for the talk.
No problem.
Just curious, have you thought about using a read replica on your Postgres instead of using Elasticsearch?
Yep, that's an excellent question. So as I said, Postgres didn't want to say Postgres was bad. We really like Postgres. And one of the reasons we really like CockroachDB is because it's quite similar to use, at least getting it out of the box conceptually, as Postgres. So we're very much fans of Postgres, and we like how Postgres can do things like the JSON-B format to allow us to intelligently store records and expand and so on. So we did consider using Postgres, using various different things, including, like you say, horizontally scaling it, having replicas and so on. But what we wanted to do is we wanted to take the opportunity to have a bit of an architectural pivot and change the direction the company was going. So this was a good project to help us to do that, to take the load off Postgres, which meant that we had a bit more time within our runway before we got more payments going through our system to look at the new build. So the short answer is Postgres could have done most of this, but we wanted to pivot.
Fair enough, thank you. And if I can sneak in a second one.
Go for it.
So I didn't see any batching when you do the inserts to Postgres. Have you considered batching, or do you not need to batch?
I'm not familiar with that. Did you say budging?
batching.
Batching, oh yeah, yeah. So we could again do that, but typically what we would find, depending on exactly how the payments are coming from the payment schemes, there would be limited opportunities to do the batching because each payment is unique. We do have workflows through our system where we do batch, so potentially we could do that in some respects, but again, we're potentially moving away from Postgres, so we didn't want to go down that route.
Yeah, I meant Elasticsearch batching, but
Okay, yeah. Within Elasticsearch, I was trying to illustrate some of that. With the multiple payments, we can do more advanced strategies as well. Yes.
Thank you.
Oh, hi, thanks. Great talk. So maybe somewhat related to that question. I'm not sure. I guess this is a demo, so I'm not sure whether the code actually reflects what you do.
Sure.
But, I'm assuming that it's quite important that the state of the database is consistent.
Yes.
So things like multiple payments coming in, but being written concurrently doesn't guarantee order. And I'm not sure whether that's something that you consider important and how you would do that.
Yes, most definitely. So again, within the context just of writing to Elasticsearch, we'd be reading the messages off the queue, and if the database has already changed state because we've got multiple readers running in, multiple mappers running in parallel, if one of them is already written and the second one gets the message from the message queue for some reason, we know that the version doesn't match, and then that one can throw away the message. And we have dead letter queues and similar things that allow us to say, okay, for this particular payment, the system has been saying that the message we read off the message queue going through the system doesn't match what's in the database. We should take a look at that as engineers. That's generally speaking what we would do in that scenario. So we would not, if we're not sure about the concurrency, we'd stop, and then we'd take a look at it, fix it, and go from there. Obviously that doesn't scale, but during the development of our initial implementation, we did that a few times. Once we'd got the system working in a smooth way, we didn't really find that problem too much. So we haven't built a lot of automation around that, but we could if it became a big problem in future.
Hello.
Hi.
Thank you for the talk. I have two questions. The first one is, would you back up Elasticsearch just like other main data stores like Postgres? And another question is, the architecture that you shared in your second or third slide, there was a relationship thing.
Yes.
So if the relationship data was on another service, so whose responsibility that would allow you to fetch that data, whether the service or the main Go microservice that writes into Elasticsearch?
Mm-hmm. So generally speaking, within the current architectures we've got the unidirectional architecture that I described. So we have everything at the moment going through the one microservice. It could be running multiple instances, but it will be handling the payments, the related documents, and so on. So I guess in terms of the answer to the second question, we don't tend to find this as a problem because we're reading messages from the message queue, we're modifying the documents, then we're changing the versions, then we're getting the related document, and we're modifying the version again. So by continually revising these aggregates and having one unidirectional workflow, one microservice that could be making these changes, it's really easy to reason about. In terms of your first question, I heard you say that you were saying, could we use Elasticsearch as a primary data store? Is that right? Yeah?
Yeah. Would you apply all the backup and disaster recovery thing to that?
Yes.
Or would you just
If we were using that as a primary data store, absolutely. Because we're using it as a derived data store to help us with certain workflows, the data is basically ephemeral. If it's lost, it's a bad thing. It can affect visibility of certain information, so we would definitely treat it as a production incident, but we could recover that data. Obviously, the primary data in Postgres is fully backed up, as you would expect. If we were to have any problems losing a particular node, because of the way we've balanced things, the cluster would reheal itself over the remaining nodes. But it can be very difficult within Elasticsearch. Once you've made a cluster configuration, if you lose a node, to change the size of the cluster, basically. So we have had to replay the data and rebuild things a few times. But yeah, generally speaking, we don't back this up.
Thank you.
Hey man, I think that was a really interesting architecture. Thanks for walking us through it. I was wondering, you talked a little bit about changing the Elasticsearch document model. I was wondering if you have a strategy for populating older documents with the new model.
Sure, excellent question. So I kind of glossed over it a little bit in my tech demo, but essentially when we're using Elasticsearch, you can think of it basically as like a column in our data store. So if you give it a document with a different shape, you can just write that straight to the data store and it will just accept it, generally speaking. Obviously, you can have problems when you're reading it. If the data is different shapes, you might have problems understanding it. But essentially, when you're writing it, Elasticsearch will just take whatever you want to give it. So to that end, we don't generally have a problem with migrating the existing documents within Elasticsearch. If we did, and we have had instances during the initial development where we changed our mind about how we'd want to store data, given that unidirectional architecture that I showed, we would just replay the payments in those cases. What would happen is when our writing service is going to write them and it can tell they've been made with an old version, it would basically write the new shape of data over the top of them. So if we had the problem you described, we'd basically repay the payment information and the data would change shape. Is that okay? Yeah.
Yeah, cool.
Cool. All right.
Hi, thank you for the talk.
No worries.
When it comes to the relationships that you're showing,
Mm-hmm.
do you ever get any scenarios where the embedded document is out of sync because of another message that's modified it and obviously duplicating that data?
Yeah, that's an excellent question. So again, we would typically have one path through which this was being updated, so we'd be able to reason about that, but the situation you described could arise, and what we would generally do is we would say that we can't process the particular message because the data doesn't match because of the ordering, as you've described. We would then take a look at that and figure out what was wrong. Because this system is used for querying very large volumes of payments, but only looking for very specific queries, we would probably look at that like the next working day. But we do have automation and alerting around that, so we'd know this issue is arising, and we'd take a look if we saw it a lot. But generally speaking, there have been quite a few scenarios, such as the one you described, and we've opted for quite a light approach that's easy to reason about, rather than building extremely heavy automation. Like the computer science is beautiful, but we don't want the architecture to grow to be massively complex. So we'd generally treat that as like a warning that we'd investigate and resolve, typically by replaying the payment again. So to be absolutely clear, these are not there's no real world outcome when we apply these payments again. It's just updating the projected data in Elasticsearch. So it's very, very trivial to replay them.
Thank you.
No problem. We've got a few more minutes, but yeah.
Hi,
No
that
worries.
was loud. Hello, nice talk. Thanks very
No
much
worries.
for that. I just was interested in how you're storing your data. So you mentioned JSON being Postgres.
Yes.
And the data that goes into Postgres. I just wanted to know, like, is that it was very interesting that you are having read issues. So like with the data on the dashboards. Mm. So are you storing the data in JSON-B format in Postgres? Is that the...
Not all of the data, no, by any means. It's kind of allowing us to evolve what's stored. So we have the critical information, as you might expect, in indexed columns. We can also use JSON-B indexes. Postgres has got an excellent story around all the different types of indexing it can do. So you can index directly into JSON-B and even index casts and so on. So queries can be really fast, but it's the joins that can be a problem. So,
okay, all right, thanks.
Thanks for that. That was really interesting.
No worries.
I was just wondering about scaling. I don't know much about Elasticsearch. Can you just keep on scaling that until infinity? Or are there kind of some hard throughput limits that you'll hit eventually?
That's a great question. I think there are definitely outer limits. I think before we hit those, we're going to probably tend to hit cost limits, where the cost-benefit analysis doesn't stack up in terms of how long we're keeping the data for versus how likely it is to be queried. And obviously we can fall back, if we can't necessarily query it from there, we can fall back to the other method for those one or two queries that might be outside the time range. So what we've generally done is we've made a trade-off between how much data we want to store and have available quickly versus, how much cost we want to spend. So yeah, I think there are definitely technical outer limits. I don't know exactly what those are, but there are some stuff in the AWS documentation, but I think most teams would hit the cost limits, the burn rate limits, far before they hit the technical limits.
Cool. Thanks.
No worries. Okay. Thanks ever so much for your time today, everyone. It's been very good to talk to you.